Hi guys, welcome on Tesla Adventures. In this video, we'll discuss the derivation and the formula for gravitational field intensity due to various extended objects. So first of all, let us take a rod, and this rod has a mass m and length L. Now we are finding out the gravitational field intensity due to this rod on its axial point. So this point P is located on the axis of the rod at a distance of x from the nearest end. This is. So we need to find out the gravitational field intensity at this point P. So as we already know that Newton's law of gravitation is not applicable for extended objects. So we just have to assume a element. Let's suppose this is dx and its distance, in fact, let us suppose it as dy and its distance is y from point P. So the mass of this element dm is m by L into dy, and the gravitational field intensity due to this small element can be written as g dm divided by y square, g m by r square. So we can write down as g dm by y square, as we have already discussed the gravitational field intensity in the previous video. So this is the magnitude of gravitational field intensity due to this element at point P. So let us substitute the value of this dm. So dm is m by L into dy, and di will be g m by L integration dy by y square. The limit of y would be from this end to this end. So limit of y would be from x to x plus L. So it is from x to x plus L. Okay, so di would be g m by L, and the integration of 1 upon y square is minus 1 upon y, and the limit would be from x to x plus L. So di is equal to this is gm by L, and by using this minus sign we can invert the limits. So it would be 1 by x minus 1 by x plus L. And in fact this is I, the net gravitational field intensity, because we have integrated di. So integration of di would give I. So this is the magnitude of gravitational field intensity due to this rod of mass m and length L at this point P, which is the axial point, and this P point is at a distance of x from the nearest end of the rod. Now the direction of this gravitational field would be towards the rod like that. So this would be I. Now let's move on the next one. Now in this case, let us find out the gravitational field intensity due to this rod of length L and mass m, but on a point which is on the perpendicular axis of the rod. It is not a bisector axis. It is not bisecting the rod into two equal parts, but it is perpendicular to the rod, and the point P is lying at a distance of x from the rod. This angle is alpha and this is beta, and we are assuming that alpha is not equal to beta. So first of all, let us suppose that to apply the Newton's law of gravitation, we have to assume a element. So let us assume a element of width dy, and this is y. So let us connect it with this point P. Now let us assume that this distance of element with point P is R, and this angle is theta. So the mass of this element dm will be equal to m by L into dy, and therefore the gravitational field intensity would be pointing towards this element di. So it is di, and di would be equal to g dm divided by r square by Newton's law of gravitation. Now the value of dm is this one. So di is g by r square into m by L into dy, and you can see that tan theta is equal to y upon x, and y will be equal to x tan theta. So dy would be equal to x sec square theta d theta, and you can also see that cos theta is equal to x upon r. The value of r will be x upon cos theta. So let us put these values, let us substitute these values of r and dy over here. So di is equal to gm by L, and dy is x sec square theta d theta, and this distance r is x sec theta whole square. So we can cancel out this sec square theta, and therefore it would be gm by L d theta divided by x. Now we know that it has two components. This is x component and this is y component. But moreover, we'll see that we'll name this component as I perpendicular because it is perpendicular to the rod, and this component as I parallel. So if I wish to find out I perpendicular, then it would be integration of di cos theta. You can see that this component is di cos theta, and I perpendicular would be integration g m by L cos theta into d theta divided by x. So in this case, this x is the distance of point P from the rod, perpendicular distance, and therefore x is constant. So I perpendicular is g m by Lx, and integration of cos theta is sin theta, and the limit of theta would be, you can see that theta is 0 at this axis and theta is negative below this axis. So we have to cover this wire starting from this point to this point. So at this point theta will be minus beta, and at the topmost point theta would be plus alpha. So the limit would be minus beta to plus alpha. So I perpendicular is equal to g m by Lx, and the limit is, this is sine alpha and this is plus sine beta. This positive sign is due to the fact that there is a negative sign due to the upper limit minus lower limit formula, and this is already negative, so this negative and negative becomes positive. So this is the gravitational field intensity due to, you can also say that m by L is lambda, mass per unit length. So this we can say that that I perpendicular is equal to g lambda by x sine alpha plus sine beta. Okay, now we can say that the I parallel component, this one, would be di sine theta, and therefore I parallel I'll write as integration of di sine theta. Now the value of di would be this one, gm by l d theta by x, gm by l d theta by x, and this is sine theta. So I parallel will be gm by lx, and integration of sine theta is minus cos theta. So this is minus cos theta, and the limit of theta would again be from minus beta to plus alpha, from minus beta to plus alpha, and therefore I parallel would be equal to gm by lx, and the limit would be interchanged due to the fact that this is negative sign is utilized. So I'll write it as cos of beta minus cos of alpha. Now you must be, in fact I'll write it here. So I parallel would be gm by lx, and by utilizing this negative sign, I'll write the limit as cos of minus beta as upper limit, and then cos of alpha as lower limit. You know that cos of minus theta is itself cos theta. So this is cos beta and minus cos alpha. So this is the parallel component of gravitational field intensity. And why we are naming it as parallel? Because it is parallel to the rod. Now there are some special cases. So let us discuss those special cases. So the first special case, you can again write this m by l as lambda. So I parallel would be g lambda by x, and this is cos beta minus cos alpha. So now let us discuss the special cases. So the first special case is the fact that if alpha is equal to beta, point is symmetric. So if I'll show you this scenario, that if alpha and beta are equal, then this point lies on the perpendicular bisector of the rod, like that, and this is equal, let's suppose alpha and alpha. Okay, so in this case you can see that the parallel component must cancel out, because the lower half will pull this point in this direction and the upper half will pull in this direction with the equal gravitational field. So the parallel component should cancel out, and let us examine this fact. So we can say that if alpha is equal to beta, so this will cancel out and parallel component will be 0, while the perpendicular component I perpendicular would be 2g lambda by x into sine alpha. We can substitute this value of alpha over here. Okay, now if second special case says that if length of wire is infinity from the both ends, so we can say that if this is infinity, then you can imagine that this wire, this rod in fact, which is of infinite length, will have both angles as 90-90. This is 90, this is 90. So alpha is equal to 90, beta is equal to 90. So I perpendicular will be equal to 2g lambda by x, as sine 90 is 1 and I parallel would again be 0. Okay, now in the third case, if the wire is such that it has a length of infinite length, but this point lies near one end of the wire at a distance of x. So in this case, this one angle is alpha is 90 and the other angle is 0 degree. So in this case, I perpendicular would be equal to g lambda by x, and I parallel would also be equal to g lambda by x. Now to predict the direction, you can see that this rod will pull these masses kept over here. So I parallel would be like that and I perpendicular would be like that. Sorry, I perpendicular is like this is I parallel and this one is I perpendicular. Okay, both having the same magnitude. So these are some cases of this rod, and now let's move on the next extended mass. Now in this case, this is a hollow sphere of some mass m and its radius is r. Now we have to find out the gravitational field intensity inside this hollow sphere. Now we have already discussed in electrostatics that the electric field intensity inside a hollow uniformly charged sphere was 0, and that was proved by Gaussian law. But there is no Gaussian law for gravitational fields, so I'll prove this fact by some other method. So let us examine a point P which is at this distance, some distance x from the center. So you can see that if we draw these two cones, okay, whose apex point is P, so you can see that the mass of this sphere lying in this cone and the mass of this sphere lying in this cone is appropriately distributed in such a way such that the gravitational field intensity due to this mass at this point and the gravitational field intensity due to this mass at this point just cancels out each other. And you can also see that if you are wondering that this mass is lower than this mass, so how it is possible that its gravitational field would be cancelled with this one. So you can also see that the distance of point P is also lesser than this mass. So it will compensate the amount of force which is less due to the lesser mass. And therefore we can say that this gravitational field will be 0 at this point, and this is true for any point inside this hollow sphere. So inside this hollow sphere, the gravitational field intensity will be 0, absolutely 0 at every point. Okay, so now if we move outside this hollow sphere, then we can say that for this outside point we can concentrate the complete mass of this sphere at the center, and hence we can apply the Newton's law of gravitation, and we can write down the gravitational field intensity formula due to a point mass in fact. So it would be Gm by r square. So outside this sphere, the gravitational field intensity is Gm by r square, and this can be deduced by imagining this complete mass to be concentrated at the center of the sphere. Okay, now if we discuss the graphical representation of the magnitude of the gravitational field intensity with r, then till the surface, this is the surface, so till the surface the gravitational field intensity is 0, because as we are starting from the center of the sphere, till we reach the surface we are moving inside the periphery of the sphere, and inside that sphere the gravitational field intensity is always 0. So we can say that till we reach the surface, I is 0, and hence just on the surface I becomes gm by r square. Okay. Now outside the sphere, the intensity, gravitational field intensity I outside is equal to gm by r square, small r square, where small r is the distance from the center of the sphere. Now this formula is pointing towards the hyperbolic relationship of I and r square. So this graph is hyperbola, and this graph is between magnitude of intensity and r. But if we draw the graph in the vector form of intensity and r, then it would be plotted in this fourth quadrant, because I would be negative. Because we all know that gravitational force is always attractive in nature, and therefore the direction of I is always towards the body, pointing towards the body. So if we examine the direction of I in this case, then it would be like that. And therefore it is just in the opposite direction of r, because r is like that. So if we write down in vector form, then I would be gm by r cube into r vector with a negative sign. This negative sign represents the fact that I is pointing just in the opposite direction of r. Okay, so this is the complete analysis of gravitational field intensity due to a hollow sphere. Now let's move on the next figure. In this figure, you can see that we are concerned about the gravitational field intensity due to a solid sphere. So it is a solid sphere of some mass m and radius r. Now, to find out the gravitational field intensity at a point lying outside the sphere, this one, we have to again concentrate the complete mass of this sphere over its center at this point, and therefore the magnitude of gravitational field intensity can be written as gm by r square, because I have considered that complete mass is concentrated at this point, and if this mass is at a distance of r from this point, so we can write that the gravitational field intensity is gm by r square. So it is just similar and just same to the gravitational field intensity due to a hollow sphere, as we have already discussed in the previous figure, and therefore we can say that this gravitational field intensity has same magnitude and direction due to a solid and a hollow sphere of same mass and same radius at a point which is at a distance of r from their center lying outside. Now, if we consider the point inside this sphere, so this is a point at a distance of r. So now we have to imagine this point to be behaving in such a way so that it is lying on the surface of this inner sphere, and this is the outer sphere. So we will find out the net gravitational field intensity at this point due to both of these spheres. So first of all, we know that the mass of this smaller sphere would not be the same. So if we need to find out the mass of the smaller sphere, we can find that the density would be m by 4 by 3 pi r cube. It is the density of the complete sphere. And therefore the mass of the smaller sphere would be density into volume. Volume is 4 by 3 pi small r cube. So if we substitute this value of rho over here, so you can see that it would be m r cube by r cube. So this would be the mass of this small sphere. Now due to this small sphere, the gravitational field at the surface would be gm by, we can also discuss that if this point P lies on the surface, on surface r will be equal to r, so I surface will be equal to gm by r square, where r is the radius and m is the total mass of this sphere. Now for this case, we can write down that the gravitational field at point P, due to this first one and due to the second. So if we write the gravitational field intensity at P due to first one, then it would be gm by r square, where r is the radius, so its radius is small r, and the value of m is m r cube by r cube. So it would be equal to gmr by r cube, I1. And the gravitational field intensity due to the second one will be 0, because this point is lying just inside the second sphere. And we have already discussed that the gravitational field intensity inside the hollow sphere would be 0. So the resultant gravitational field intensity would be gmr by r cube. And if we write it in vector form, then it would be like that. Okay. So if we plot the graph between these two, so inside you can see that I in is gmr by r cube. So this is proportional to r. So it would be a straight line whose slope will be tan theta will be equal to gm by r cube, and afterwards it would be a hyperbola because I outside is gm by r square. Okay, now let's move on the next figure. Now this is a ring of mass m and radius r, and we have to find out the gravitational field intensity due to this ring on axial point. This point P is situated at a distance of x from the center of the ring, and to find out the gravitational field intensity, we need to assume an element of length dl on the diametrically opposite ends of this ring. So we have assumed this element, and let us first of all connect the point P with these points, these elements. So this is the distance. Now this distance is, let's suppose r, so r would be equal to under root of r square plus x square. The gravitational field intensity due to this elements at point P is like that. This is di and this is di. Okay, and this angle is phi and this angle is phi. So the component of these di's along the axis is 2 di cos phi, and this component is di sin phi, while this one is di sin phi. So di sin phi would be cancelling out with each other, and the net gravitational field would be 2 di cos phi. But first of all, let us write down the value of dm. So dm would be lambda into dl, where lambda is mass per unit length, which is 2 pi r. So dm will be equal to mdl upon 2 pi r. Okay, so di will be g dm divided by r square, and di therefore will be g dm. Dm is mdl by 2 pi r into r square. Okay, so you can see that the value of r is not the part of integration because it is constant, as r is constant, capital R, and this x is constant. So the total I would be integration of 2 di cos phi. Now cos phi is also constant, as cos phi is equal to x upon r. So you can substitute the value of cos phi, and this would be I is equal to integration 2. This is gm by 2 pi r into cos phi. Cos phi is x upon r. So this is r cube, because already there is r square and this is r, and this is dl. Okay, so this is if we take out gm by pi r common by cancelling 2 with 2, and x by r cube common, then the integration of dl will be equal to L, where dl is small elemental length on the ring. So this is gmx by pi r, and this is r cube, and its integration would be L, and the limit of L would be 0 to pi r. I have not taken 2 pi r due to the fact that I have already assumed two elements on the diametrically opposite ends. So I would be equal to gmx by pi r into r cube into pi r. So cancelling this pi r with pi r, I would be gmx by r is x square plus r square to the power 3 by 2. So this is the gravitational field intensity due to a ring, and now we will discuss its graphical variation with r, in fact with x. So now let's move on that. Now while representing the magnitude of in fact the gravitational field intensity with r for a ring, you can see that if I is equal to gmx by x square plus r square to the power 3 by 2. So if we write it in vector form, then there would be a negative sign. This negative sign states a fact that x and I are in opposite direction. So therefore, you can also see that at center, x would be 0, so I would be 0. Okay, now at infinity also, x tends to infinity, I would be 0. So the gravitational field intensity would be 0 twice, once at center and once at infinity. Now if we plot this graph, then for positive x-axis, this graph would be plotted in fourth quadrant, and on negative x-axis it would be plotted in second quadrant, because in this case I is negative, or I can say that the direction of gravitational field intensity is in this direction, backward direction. In fact, for the ring I was talking that it would be in backward direction, but beyond this point, like I can say that if this is a ring, then the gravitational field intensity at this point is pointing in backward direction, while at this point it is pointing towards this in forward direction. So for negative x, this is I is positive, and for positive x, I is negative. So this graph represents the gravitational field intensity. Now if we wish to find out these points where it is maximum, then we can easily find it out by maxima minima and by differentiating this intensity. So these points would be plus r by root 2, and this would be minus r by root 2. So at this point, the I would be maximum, and we can also find out the maximum value of I, and this is the graph of graph of gravitational field intensity of a ring plotted with x or r. Now let's move on the next figure. Now it is a disk of some radius r and mass m, and we have to find out the gravitational field intensity due to a disk on its axial point at a distance of x. So in this case, we have to assume a element which is a ring in this disk, because we already know the magnitude of gravitational field intensity due to a ring. So let us assume a ring of radius small r and width dr. So the mass of this ring dm would be mass of complete disk per unit area into area of this elemental ring. So area of this elemental ring will be 2 pi r dr. You can understand that. So cancelling this pi with pi, so dm will be equal to 2m r dr by r square. Now the gravitational field intensity due to a ring has a formula of gm x by x square plus r square to the power 3 by 2. So if we apply it for this element, then it would be g dm and x upon x square plus its radius is small r to the power 3 by 2. Okay, so this is the formula for elemental ring intensity. Now total gravitational field intensity would be g dm, where dm is 2m r dr divided by r square into x square plus r square to the power 3 by 2. Now you can integrating it. Now you can take out the constant terms, and this is 2 gm x by r square, and it is r dr upon x square plus r square to the power 3 by 2. So limit would be from 0 to capital R, because the radius of the smallest ring would be 0 and the radius of largest ring would be R. So I would be equal to 2gmx by r square, and to integrate this expression, we need to consider that let x square plus r square is equal to z square. So 2r dr is equal to 2x dz, 2z dz. So cancelling this 2 with 2. So let us substitute these values. So this is 2gm x by r square, and this is integration r dr, which is z dz, and the value of this would be z cube. So you can cancel out this z with this one. This is z square. So I would be 2gmx by r square, and 1 upon z square integrates to minus 1 upon z. So limit would be from 0 to r, but we have to resubstitute this value of z which we have assumed, and it was this one. So z is 1 upon under root of x square plus r square. We should always remember a fact that we have a integration variable as r. So we have to substitute the limits in the place of r. And by using this negative sign, this one, I am just reversing the limits. So limits would be 0, r to 0. So this is 2gmx by r square, and this is 1 by x minus 1 by under root x square plus r square. So conclusively, if I say that the gravitational field intensity due to a disk would be this is 2gmx by r square, and this is 1 by x minus 1 by under root of x square plus r square. So this is the gravitational field intensity due to a disk of mass m and radius r. Thank you.